Hey everyone, my name is Lucas. I'm the Senior Program Manager Lead for the Windows AI Platform team. So far at Build, you may have noticed the theme, AI. We've done a lot of talking about AI, both on the intelligent cloud and now on the intelligent edge. Today, I'm here to talk to you about the Windows AI platform on the intelligent edge. So, with a quick show of hands, how many of you today do some sort of machine learning or AI technique in your current applications? That's awesome. That's almost like half of you. That's great. For the other half, you may be wondering, as a developer, why should I care about AI? Half the people in this room already do. And the simple reason is, as developers, we're often asked to solve incredibly hard problems. For instance, some of these problems are very difficult to solve when the only tool we have available to us is traditional algorithms and procedural code. Consider the sort of code you would need to write if, in your line of business application, you are asked to classify whether a specific customer may be a retention risk for renewing their services with you or not. Imagine the code you would have to write if, in your application, you had to take a specific action, but only if a particular condition or object was detected in an image or in a video stream. Maybe in your application, sometimes you're asked to find a defective part, as that part moves quickly across a manufacturing process. These three problems have one thing in common. They're somewhat easy for humans to solve with human intuition, but each one of them is incredibly difficult to program a computer to do. This is especially true, again, if the only tool we have available to us are traditional algorithms and procedural code. This is where AI can help. And we know this because at Microsoft, we're using AI today to solve some hard problems. Here's one example. The Windows Ink platform uses AI techniques today to figure out conceptual meaning from physical ink strokes that you as a user may draw on the screen. Using AI techniques, the Ink platform today can figure out whether a set of strokes represents text or whether it represents shapes. With this knowledge, we can now start figuring out, is this text part of a word? Knowing that something is a word, we can start figuring out, is this word part of a longer sentence? Knowing that, we can do more conceptual understanding and figure out, are these sentences part of a paragraph? And when you think about what else is happening in this diagram, some of these lines have little annotated bullet notes next to them. And using AI, we can figure out, hey, these lines seem to be part of a list, and we should conceptually think of them as a list. All of these inferences are incredibly difficult to do using traditional algorithms. But with AI, we can do it. And because of that, we can go the next step and figure out additional things. For instance, there's some text up here that looks like a phone number. Using AI, we can understand that this may be a phone number, and it may be associated with, I believe Tom's name is somewhere in this doodle. And now that we know that, we also see that it looks like there may be an invite to an event 1 week away. Again, figuring out all these conceptual properties from just physical ink strokes is incredibly hard if you don't have AI to help you. As you've heard in the keynotes this morning, Microsoft has made a lot of investments in AI. And we've worked with developers across the industry to understand what AI solutions developers need. Many of Microsoft's investments to date have been in the Azure cloud. We have a set of products that can help you do many different things. Azure Cognitive Services gives you cloud-based pre-built AI APIs that you can use in your application to help you solve hard problems with vision, speech, language, search, and others. Custom Vision allows you to create models that are tailored to your unique scenario to help you identify objects in pictures. Azure Machine Learning Services gives you an end-to-end solution for preparing your data, using that data to create your AI, and being able to deploy that AI to fully managed web services. And likewise, if you're more of a do-it-yourselfer, Azure Batch AI gives you infrastructure where you can scale your AI training in the cloud across a bunch of machines that have GPUs. But as developers, we sometimes need these AI capabilities on our edge devices where our application runs close to the data. There are 3 reasons for this. First, low latency. Sometimes we need real-time results. For instance, if you are evaluating whether an object appears in a video stream, you can't necessarily wait for the round-trip cost of time to the cloud in order to use AI to tell you that, yes, in fact, the object that you care about is in this image. It's also true if you're trying to use AI in really high-performance scenarios. For instance, imagine using AI to power your game engine so that the non-player characters do intelligent things. The second reason is scalability. If today you have a service that's already deployed at scale, and you are looking to add intelligence into that service, being able to do AI processing on the edge where your service runs allows you to optimize your operational costs. This is because you only have to worry about spending money to train that AI in the Azure cloud. And you don't necessarily have to worry about every AI operation getting sent out to the cloud for evaluation. The third reason why AI processing on the edge is important is flexibility. Sometimes our data is just going to be too large to send off to the cloud. Other times, we may just not be connected to the cloud. How many of you flew into Seattle today? Only one person? That's amazing. That person may not have had Wi-Fi on the flight that they came in on, but we still want our applications to do intelligent things for them, even when they're 40,000 feet in the sky. Likewise, whether due to customer policy or preference, sometimes we just can't send the data off the device to the cloud for AI processing. So when we think about bringing AI processing to the edge on Windows, there's 3 things that we think about from a Windows AI platform perspective. 1, we want to give you developers a platform that you can easily use to bring powerful, intelligent experiences into your applications. 2, we do it in a way where we can use those exact same tools in that exact same platform to help improve Microsoft products, make Windows smarter, and all of our products smarter. And 3, as you heard in this morning's keynote, we want to make sure that a Windows AI platform integrates fully with all the Microsoft AI offerings that we have, both on the intelligent cloud and on the intelligent edge. I'm happy to say that in the Windows 10 April 2018 update, we're releasing Windows ML, a new API that allows developers to use pre-trained machine learning models to evaluate hard problems on the edge while using the full hardware capabilities that are available on that end node. This is a unique offering from Microsoft because we are in a position where we can train models in the cloud, bring them down to the edge where you can evaluate them with Windows machine learning, optimized down to the silicon level. Let me show you how. Here's an application that we have that does something called style transfer. You may have seen applications like this before. What they do is take an image and apply a visual style to it to produce the image on the right. This one particularly is using Windows ML to power this experience. And because it's using Windows ML, there's a couple cool things to note. First, every single one of these visual styles, like you've seen just change over, I actually didn't have to write any new code to do. Each one of these output images has been generated by the machine learning model that's been trained over diverse data sets from famous artworks. When you think about the advantages of the intelligent edge in this case, I would not be able to do this scenario taking input from the camera stack and doing this very computationally expensive processing on it with as fast frame rate as I have right here, if the only tool I had available to me was to send it off to the cloud for evaluation. 2, each one of these frames is fairly large, and I'm sending a lot of them for processing. Again, from a scalability perspective, I may not be able to push all of this data off the intelligent edge. And 3, for those of you who have maybe walked by the Windows AI platform booth in the expo hall, I may have asked you to dance in front of this demo just for fun. And you have to ask yourself a question. Sometimes, do we want images beamed off the device, especially when we're doing something as silly as this? That's where having the intelligent edge really helps with your applications. And because this is using Windows ML, there's also a few more nice features to note. First, we've optimized the path from the camera down to the GPU where this model is being evaluated. That means we've gotten rid of as many redundant copies and streamlined the path as much as possible. 2, this is right now running on the NVIDIA GPU that's inside my Surface Book. However, I can take this exact same app and run it on any DirectX 12 GPU to get hardware acceleration. As a developer, my code doesn't change as the app moves across the diversity of the Windows hardware ecosystem. Let me show you how I did this. As I noted before, every single one of those visual outputs was the result of a machine learning model evaluation. Machine learning is a very powerful tool. It works by finding patterns in existing data so that when new data is given to a machine learning model, it can use that previous experience to identify new patterns. We have a saying, when the solution is difficult to describe the data instead. And what we mean by that is, if in your line of business application, if you can ask yourself, what is the really hard problem that my application is trying to solve, and phrase it with clarity. And then, if you can go off and identify a data set, an existing data set, that is pre-labeled with the desired result, you can use machine learning to help you find the new pattern in new data when you get it. For example, now I can ask myself the question, will my customer renew their services? And if they do, which services will they renew? If I have existing data that showed which customers tended to be ones who left my service versus ones who stayed, I can use that data to train a model that will help me answer this question in my application running on the edge. Let's review the conceptual pattern at work here. We call this from ideas to inferences. We start with our application. Again, in our application, we ask, what is that hard question? Once we've identified that hard question, we can find the data that's pre-labeled with our desired result. And we can take that to the many offerings that Microsoft has in Azure to help us train a model. So for instance, we could use Azure Machine Learning Services. We can use Custom Vision. And the output of that training is something called a model. In this case, you see that the model has the word ONNX underneath it. I'll tell you more about ONNX later. For now, all you need to understand is that it's an industry standard model interchange format. Once you have an ONNX model, Visual Studio makes it easy for you to start adding intelligence to your application. If you are writing a UWP project, when you add an ONNX file to that project, Visual Studio will automatically generate Windows machine learning inference code for you. This is all code that you could have written yourself. However, Visual Studio makes it convenient for you. Now that I've added that ONNX file to my application, I can start wiring up my application data, that new data that I want to find a pattern over, into the Windows ML API calls. And because I'm using Windows ML, I know that model will be evaluated on the full diversity of the Windows hardware ecosystem using any DX12 GPU without me having to write any different code to handle a specific different GPU device. Pardon me there. So when I was writing that style transfer app, Windows ML helped solve 3 problems for me. First, as a developer, I didn't have to worry about creating each one of those visual styles myself. I could focus on the data that I have and the scenario that I wanted to enable. In this case, a visual style transfer. Windows ML has a built-in evaluation engine in Windows, which allowed me not to focus on infrastructure and deploying machine learning engines, but just focused on scenarios. 2, Windows ML enables me to use models trained in a variety of different frameworks. So long as I can get that model into an ONNX file, I can use it with Windows ML. 3, Windows ML offers hardware acceleration to get me fast evaluation results. And we do this across any DX12 GPU. Because we use DirectX, a lot of you in this room may know that it has a proven history of high performance across a wide range of devices. And we do this by offering both a Win32 and a UWP API for you to use. So, half of you in this room raised your hand previously saying that you're using some form of machine learning solution in your application. I want you to think about how Windows ML can now make your lives a whole lot easier. When your data science organization brings you a set of models that they want to see used in your application, you no longer have to worry about, well, how do I get the complementary evaluation library deployed with my application to evaluate that model? Windows ML does it for you. Likewise, if you need hardware acceleration, in the past, you would have had to code against specific third-party SDKs. With Windows ML, you don't need to do that anymore. I'm about to jump into some code, but let's review the Windows ML calling pattern before I do. There's 4 steps. First, you use the Windows ML API to load a model from an ONNX resource into memory. You then wire up your application inputs into the inputs that the model expects. For those of you who aren't familiar with models, at this stage, just think of models as a function. They take inputs, they take outputs, and inside they encapsulate a bunch of functionality. Once I've wired up my inputs, I can run evaluation on that model to generate outputs. And then I can interpret those outputs to drive my application experience. Let's put it all together with a quick code sample. On the screen, you see a very simple UWP application. There isn't too much special going on in the UI. It's a simple in-canvas control and a couple of buttons. However, we wrote this app such that when a user draws something in the in-canvas control, we can use the MNIST model, which is a model trained on a wide variety of handwritten images, to detect what digit the user has drawn. I mentioned earlier, Windows has a very good ink platform, and this isn't how you should go think about doing ink in your application. But it's a very good example of how Windows ML works. So if I, for instance, draw a 3 in this ink canvas, and I hit the recognize button, in this case, it thought it was a 2, but that's more of a statement of my poor penmanship. So let's draw a 2, and it thought it was a 2. Now I'll try a 4, and Windows ML, evaluating this model, determined that I had drawn a 4. Let me show you the workflow to actually get this going. This is the Visual Studio solution for this project. I'm not going to show you code in Visual Studio. I'll do that in the PowerPoint deck because it's easier to read. But I want to show you how easy it is to get started with ONNX models in Visual Studio. For those of you who may have a hard time seeing the mouse, I'm right-clicking right now on the Assets folder to add a new existing item. I'm going to navigate to a folder where I know my ONNX file lives. And I'm going to add it. Before I do, I want you to notice that in the list of files, there's going to be a new file that appears as soon as I do that. Awesome. And when I did that, mnist.cs appeared. Let me show you what the code that was generated looks like. Visual Studio generated 3 classes for me within mnist.cs. These are the first 2. One of them is an input class, and the other one is an output class. I'm going to really geek out here over a couple of properties, but bear with me for a sec. The first thing you'll notice is that there is a getter-setter property for something called input3 that takes a video frame as a data type. Now, input3 was actually the named input that the model described. Windows ML using Visual Studio code generation tells me what that name is. I could have also used other tools like Netron to inspect the model, find out its metadata and properties. The important thing to note on this line is the data type, video frame. Machine learning models in general do not understand images. And my application actually created a software bitmap of the ink canvas before I fed it into my machine learning model. However, since machine learning models don't tend to understand images, rather very long tensors of individual pixel data massaged into this long list, it creates a problem. That's not how developers actually code against images. Windows ML makes working with image models easy. Video frame is a common data type to get an image source out of a camera or a bitmap on disk. Underneath the covers, when Windows ML detects that you're loading an image model, it specifies video frame as an input type. When you give it a video frame for the input, Windows ML will automatically convert that image into the tensor layout that the model expects. It does another thing for you that's really handy. Models rarely work on the full-sized image. A lot of models just expect a very small cropped version of the image, something like 224 by 224 pixels. As a developer, we don't want you to have to spend time inspecting the model to understand exactly the size of image that it expects. So Windows ML does it for you. When you hand in a video frame as an input, we will automatically scale and crop the image to what the model expects and lay it out in that tensor format. Moving on to the output class, you'll notice right now that it's purely a list. The outputs from models can be one of several different data types. In this case, I know this model returns me a list of 10 items. The list will be the probabilities that the model thinks are what I had drawn, the digit that the user had drawn on the screen. The index of the highest probability corresponds to the digit. However, other models will return different data types. So for instance, classification models that can tell you the types of objects that are in images will actually return dictionaries that are already pre-labeled for you, so you know which label corresponds to which probability. Moving on, there's one more class that Visual Studio generated for me. And this one does the heavy lifting. So much so that the curly brackets are a little strange in the slide, but I'll need the next 2 slides to explain this. The first bit of code just takes a standard UWP storage file, which is the model asset that I've included with my application, and loads it into memory. It loads it asynchronously, so my application remains fluid throughout this whole process. And in fact, all of Windows ML's operations are asynchronous. Once I have this model loaded, I can call evaluate to actually start getting answers to my question. You'll notice one new concept in this slide, something called bind. In order to feed your application inputs into a machine learning model, you need to wire them up. We do this by binding. So in the 2 lines that bind the input and the output, you see that the generated code has actually taken the named properties that the model was expecting, input 3 and something called plus 214 with a lot more characters afterwards, and binded my specific application data to it. Once that's done, I can just call evaluate async, and that will automatically populate the output class with the model's results. This is all code that you didn't have to write. As soon as you added an Onyx file to your project, Visual Studio just did it for you. Let's look at the code that you actually had to write, and it's not a lot. So, I'm not going to speak too much to the initializations. We're using windows.ai.machinelearning.preview. Windows ML is in developer preview in the April 2018 release. I then have some code that takes a storage file and actually loads the Onyx file, which I then hooked up in the generated code. And this is where the real action happens. This is the click event handler for my application. So when I clicked recognize in the app, here's all the code I needed to do in order to get an answer from my machine learning model. The first line is just a quick helper function that I wrote that took the ink canvas output and saved it as a bitmap in memory so I could use it as a video frame into my evaluation. I called evaluate async. And the next 2 lines are just me interpreting the results from that model. That's it. In less than 11 lines of code, I have actually evaluated a machine learning model with Windows ML. And the really amazing part is, if I added one more line to say that I wanted this evaluation to run on the GPU, it would run on any DirectX 12 GPU. It's super easy to use. Now, you've heard me use the word ONNX several times. I mentioned before that it's an industry standard for model interchange. It's actually also a community project started by Microsoft and Facebook, which defines a computational graph and a set of defined operators that can be used within that graph. This format supports a wide array of machine learning models, from classical ML to convolutional neural networks. And you can learn more about it at onnx.ai. But you want to get started with your application. So you're probably wondering, well, how do I get these ONNX models? The easiest way, if you just want to start playing around and exercise common scenarios, is to use the curated experience on Azure AI Gallery, which has a set of ONNX models that you can use in your application with Windows ML today. Azure Custom Vision Services allows you to easily take a set of images and train your own image classification model. So you can use the output of that process to figure out things such as, is there a surface book in an image that I'm looking at? And I'll show you that in a little bit. Azure Machine Learning Services, as I mentioned before, is an end-to-end solution to help you prepare your data and train your own machine learning model that you can then export in ONNX and use Windows ML on the edge. And if today you have existing model assets in one of several different formats, be it Core ML, scikit-learn, libsvm, we have a converter tool, which is a Python package called WinML Tools, that you can use to convert those models into ONNX to use in your application. Let me show you a couple of these ways of getting models in a few conceptual examples. The first example I want to show you is how easy it is to write your own application that does image classification on the edge where your application runs. In this app, we've trained a machine learning model using customvision.ai to recognize whether a device that's in the picture is a Surface Pro or a Surface Studio. Here you can see that when I fed it an image, it was able to use that model to decide with a probability of about 99% that in fact there is a Surface Pro in this image. The really awesome thing is, with all those optimized camera paths and fast GPU acceleration, and also optimized instruction sets on CPUs up to AVX512, I can also do this on video. And I'm hoping the demo gods are friendly to me, because this is a risky demo to do under these lighting conditions. But remember, this model is trained to detect whether there's a Surface Pro or a Surface Studio in the image. Right now, the model is not detecting anything. Let's see what happens when I bring up a Surface Pro. It can now detect that there is a Surface Pro in this image. And the really exciting part is, all I needed to do to create this experience was use a data set of about 30 images fed into Custom Vision to create that model. This model took me minutes to create. And if you actually want to figure out the full end-to-end details of how to use this, we have a great session on Wednesday about visual intelligence and adding it to your UWP application, where you will use this as a sample lab. Remember, this model took me minutes to make. And it took me the same 11 lines of code to actually use in my application. It's just as simple as that MNIST example. So with a very low investment, you can now, using end-to-end Microsoft technologies, evaluate image classification models using the hardware that's available on the end where your application runs. But let's consider a different example. I showed you that the model could detect the Surface Pro. But what if I happened to have held up an Xbox? Today, the model would have said there's nothing detected, because the model was not trained on any images of Xboxes. One of the patterns that you guys can use to help make the model better over time is to then ask a user when something is not detected to help you label that data. In the previous application, I could have easily added some UI that would have saved the image for me when something was not detected, and exposed the set of options that a user could have selected to label the image. Once I've accumulated enough of these samples over time, I could feed them back to custom vision services in order to train my model, such that next time when a user held up that previously undetectable object, they would now be able to detect it using this model. From an application code perspective, 0 code changes. Beyond adding that UI, you would have to do absolutely nothing different to evaluate that model. But you may be wondering, images are awesome. My application doesn't need to classify images. But I do need to solve other hard problems that may depend on a lot of data. And we have an example for that too. Here's a very simple application. The UI is so minimalist that it's almost distracting. However, you'll notice that as I start sliding my finger across the UI, the bottom of the page changes the label to identify what kind of flower subspecies the petal measurement that I just had modified, the sepal width measurement that I just had modified, may classify to. Now, you may be wondering, why am I talking about flowers? The important concept to remember here is not that I've written an app that you can use to identify what particular type of flower maps to a certain measurement. The important concept here is that you can do this with your data just as easily. This application underneath the covers, again, just took a model and is using Windows ML to evaluate it. I am doing nothing specific for flower detection. Let's look at the data that was needed to generate something like this. This is the iris data set. It's almost the hello world of the data scientist world. It's such a famous data set that was collected back in the 1920s on various flower measurements that it's actually used as the getting started tutorial for Azure Machine Learning Services. If you follow that tutorial and bring your own business data to answer your own hard business question that's pre-labeled in the same way this is, you in your own applications can use a machine learning model, again, with the same 11 lines of code that it took to operationalize every other model I've shown you, to power your experiences. That is really, really powerful stuff. Now that I've shown you a couple examples of how easy it is for you to add AI and ML solutions into your application, I want to show you a couple of examples of how we're using it at Microsoft today. The first one is from our Windows Photos app team, who in the April 2018 update, updated the Windows Photo app to use Windows ML to classify images. Here's what they had to say.
We all have so many photos, and we want to help you find people, places, and things you care about in the photos, help you tell your stories, and also add a little magic with 3D special effects.
The first time I integrated WinML into our product, I quickly saw 20% increase in performance. And when I turned on the GPU, we saw 80% performance increase.
WinML saved us a ton of time. We were able to focus on our data, our models, and our user scenarios, rather than store compliance and how to run across hardware. WinML has allowed us to experiment with doing skeleton tracking with your basic webcam. Our group decided to dance in front of the camera, and we're able to track joints and movements.
WinML is groundbreaking. It is the first API that allows everyone to evaluate machine learning models, both for UWP apps and desktop apps. It's also accessible to all developers. It allows developers to seamlessly use CPU and GPU to evaluate their models.
We're so excited about the WinML update because we'll get to focus on our scenarios, our data, and our models, and WinML takes care of the rest.
We can't wait to see what others can do with WinML.
And you can use that today. There's a second example that I want to show you that's more of a proof of concept. You may have heard about a new feature in the April 2018 update called Timeline. Timeline is a powerful organizational tool that allows you to see what activities you were doing on your PCs in the last day, in the last week, in the last month. It does this by creating a set of tiles for each one of those activities, creating this very visual experience. Now, one of the really hard things is a lot of these images are sourced from the website that you happen to have visited to represent that website. And not all of those images are going to be perfectly composed. So when Timeline gets an image that's slightly too big to fit inside the tile that it wants to show, it crops the image. And today, it does this by cropping on the top left-hand corner of the image to the extent that it needs. However, sometimes this can create slightly misframed images. So for example, in the bottom left-hand corner here, you can see that at some point I went to Wikipedia and I looked up sheep. And in this case, instead of getting a picture of sheep, it actually ended up cropping to the top of the image, which happened to be more mountains. Looking at some of the other images, you could see that the car and the motorcycle in the middle images are cropped somewhat strangely. Their wheels are cut off. Again, Timeline today has no knowledge of what images or what objects are in the images that it shows for its UI. So it's hard to figure out where to crop the image. Let me show you a proof of concept that the Shell team recently implemented, which uses Windows machine learning on each one of these images to identify the location of certain objects in those images to create a way better framing. And for this, I'm going to switch to my demo machine quickly. So here I am, just a new VM. And when I go to Timeline, some of those websites that I had previously visited now have much better visual experiences. For instance, the image of the motorcycle and the car is now way better framed. It's because Timeline used Windows ML and evaluated a model on the edge using the GPU to determine that there is a meaningful conceptual object in this image and should crop around it as opposed to potentially bisecting it. And just to show you this is for real, last night with all the excitement around Build, I couldn't fall asleep. So I started going on Wikipedia again and reading up about sheep. Hopefully it would help me count sheep and help me fall asleep. So here was the article that I looked at. And now remember, in the previous example, the picture that Timeline used focused more on the mountains and cut off a lot of the sheep. But now if I close Wikipedia and go back to Timeline, you can see with Windows ML, it has created an image that's cropped on the subject matter in the image. This is really powerful stuff to be able to do on the edge, because there's no way that we could deliver this sort of experience for all of our users without having Windows ML. Everything you've seen so far is available today in the April 2018 Windows 10 update. But I mentioned at the beginning, we are the Windows AI platform team. And as a platform team, it's our never-ending goal to make sure that Windows ML can be used by you guys to make your product successful. Our platform will keep evolving. And I want to give you a sneak peek of some of the things we have in our roadmap. I mentioned earlier that Windows ML today is in a developer preview namespace. We are working hard in our next release to take it out of preview. This is more than just a name change. Ever since Windows ML was announced publicly back in March at the Windows Developer Day, we've heard some really great and insightful feedback from developers in the Insiders program. And we've used this feedback to improve the platform. When Windows ML comes out of preview, we will have added functionality in order to allow you to load a model from a stream, so you don't just have to depend on storage files to do so. Another commonly requested calling pattern of Windows ML is developers have found that it's rare that you just have one model that runs your entire experience. Usually what you're doing, actually, is evaluating multiple models in series. The calling pattern of Windows ML today is such that you load a model, bind, evaluate, get the outputs. And you could do this asynchronously for multiple models at the same time. But we wanted to make sure that the platform was as optimized for this calling pattern as possible. So we are looking at what it means to allow you to chain multiple model evaluations together such that the hardware can constantly get utilized without any sort of breaks and work with that calling pattern that's more natural to developers today. In future releases, we are looking at adding new model capabilities. Today, Windows ML supports the evaluation of models with floating point 32 data types. Onyx, the underlying format, supports data types of FP16. We're looking to add this support to Windows ML so the model files that you use can become smaller, and also so when they're loaded into memory, they take up less space in memory when your application is running. Likewise, as awesome as Onyx is for defining a standard operator set, this is a very fast-moving space. The research community is constantly coming up with new models, and within those models, new mathematical operators to drive the experience. We want to make sure that Windows ML can evaluate models that are on the bleeding edge. And we're looking at what it means to add custom operator support into Windows ML. What that means for you is you can use Onyx models that define operators beyond the standard Onyx operator set and still have Windows ML evaluate those because you can provide the implementation for that operator. In future releases, you will see even faster hardware acceleration. Today, Windows Machine Learning can evaluate a model on any DirectX 12 GPU. It uses DirectX and specifically Direct Compute to implement every single one of the Onyx operators so it can run on a wide, diverse set of GPU hardware. However, we know GPU vendors know their hardware best. And for some of these operators, they actually have optimized paths that they use on their device in order to get even better performance than our broad implementation. In future releases, we are looking at means of having the GPU be able to provide those optimized paths, such that from a developer perspective, your code never changes, evaluation just gets faster. And you never have to worry about specifically what device you're running on. You'll just always get the best performance from Windows ML. Lastly, back in March on Windows Developer Day, we showed you some exciting early work that we were partnering with Intel on in order to be able to do Windows ML machine learning evaluations on the Intel Movidius VPU. This work continues, but it's very important work. From a developer perspective, no matter where your model is being evaluated, we never want to see you guys have to write code that's device specific. And because of this, I'm happy to announce today that Microsoft is also working closely with Qualcomm to bring Windows ML support to the Snapdragon chipsets. So we're getting near the end of the talk, and the one thing that I want you to walk away with is you should go out and try Windows ML. If you want to learn more, you can go to this URL, which is our current documentation, to learn much more about Windows ML. You can explore the full set of Microsoft end-to-end AI solutions, and this conference is a great opportunity to do that. From Azure Machine Learning Services, Custom Vision, Azure Batch AI, all the way down to the Intelligent Edge with Windows ML. For those of you who today work with a data science organization, and again, you may have a problem where those organizations provide you models in various different formats that then make it difficult for you to operationalize them in your application. Talk to your data scientist about Onyx. Onyx will make it easy for you to use that model with Windows ML to get hardware acceleration on the edge. If you have questions, thoughts, feel free to reach out to my team on askwindowsml@microsoft.com. And lastly, we have a booth in the expo hall. Please come visit, say hi, ask us any questions you have. And as always, please complete your session evaluation. We really value your feedback to make these experiences better for you. Thank you. Question?
All right. How does the WinML tie in with ML.NET?
Sure.
Is it the same thing? Is it the same thing? Or
It's not the same thing. So ML.NET has been recently announced to help you use C# in order to be able to train your models. Part of training is also being able to evaluate your models. So the whole goal of that effort is to allow developers who are familiar with C#, who want to start doing model training, to be able to do that from the environment that they're familiar with. Windows ML is an API that you can take the outputs of that training and use in your application to get hardware acceleration for model evaluation. Windows ML should be thought mainly as an evaluation platform. ML.NET should be thought of as a training platform. Question number 2. You, and then we'll come back to you. I'm sorry, I couldn't quite hear that question. Is that microphone actually working? Yes. How about we line up at the microphone? We'll start with you.
Okay. So what control do we have as developers on the underlying ML technology? Like if you want to say we use marginal space learning or boosting trees or deep learning, do you give any sort of control?
Sure. So the question that you're asking is probably more catered towards training. Those are all techniques used to generate a model. Once you have that model saved as an ONNX file, when you give it to Windows ML, it handles like how to load it into the engine, how to build out the computational graph, and evaluate every single one of the operators in that graph. So you actually don't have that control because that's more of a training affordance than an evaluation affordance. Once you have that model, Windows ML is good to go. Thank you.
So what's the plan to support the Windows 10 IT Core?
So this actually works on IoT today.
Today?
Yes.
Does it support ARM v7 devices like Raspberry Pi 3?
I don't know about Raspberry Pi, but it does work on ARM today.
Okay. Thank you.
Yep.
Hi. There's a great diversity of GPUs out there. What's your min spec for GPU acceleration? And
If you have a DirectX 12 GPU, Windows ML can run on it.
Okay.
If the question is more around performance, that's going to be highly contextual to the model and the network that you're trying to run. However, if it's a DX12 GPU, you can try it out and gauge whether the performance is adequate for your scenario.
That was sort of my follow-up question. Do you have any sort of data that sort of shows how performance would scale in a given application via different GPUs, integrated GPUs, discrete, and so forth?
I don't have data on hand. Conceptually, though, obviously, the more teraflops you have, a lot of this is matrix math. It would scale with teraflops.
Fair enough. Thanks.
I'm short.
No worries.
Is it open source?
Windows ML is not open source, no. It is part of the Windows operating system.
All right, because that was the next question, if it's tied to Windows, because the name sort of indicates that.
Yes. So Windows ML is a platform feature within Windows. The evaluation engine is actually built into Windows, and the API ships as part of our SDK. ONNX, however, is an open source project, so the model interchange that we're using is. Thank you.
Hi.
Hello.
We have a Windows ML and Azure ML, so how can we get benefit from both? Is it possible to do that?
I'm sorry, can you step a little closer to the microphone?
We have a Windows ML and Azure ML, right?
Sure.
So how can we get benefit from each other? How can we integrate both in the same thing? I mean, any device or IoT?
Gotcha.
Yep.
You should think of them as complementary affordances. Azure Machine Learning Services are a great way for you to start training your model and generate that ONNX asset. If as a developer, you feel the need to then take that model and deploy it into one of Azure's managed web services because that is the flexibility you need in your app, that's great, do it. If you have a need to be able to take that model to an edge device because perhaps that device can't send data off of it or just isn't connected, Windows ML allows you to do that on any Windows device. So you should think of them as complementary evaluation platforms. And Azure ML also is an amazing training environment to create your model.
Okay, all right. So how to generate that ONX file, I mean, from Windows ML?
I'm sorry, I couldn't hear that question.
You generate the ONX file for the image processing point of view, right? So if you want to put that some security, I mean, and security processing systems, suppose if I create some hypothetical apps like, my virtual guard, right? House guard, right? So which is, opening the door through IoT based on the image, right? Which is a house owner, right? Or maybe the house members. So they can do that, right? So can we build that, something like this?
You know what, can we jump into that question after the talk? I would love to understand it a little bit better, but I'm just having a hard time hearing the microphone right now. But if you can stay around for another 5-10 minutes, I'd love to help you address that question.
Okay, all right, yeah.
Thank you.
So a couple of questions. Do you plan to support heterogeneous computing, like CPU, GPU running from the same model, or breaking the one model into multiple models itself?
That's something that we're always thinking about. Like, there is a trade-off to be made when you do that. Sometimes the cost of moving resources between sort of the centers of processing actually makes doing the evaluation across multiple places less advantageous than one would think. But it's something that we're thinking about. We don't have plans right now.
Okay, and for the custom primitives, like cutting-edge primitives, which is not supported, maybe in ONX but not in WinML, can we add new language? Like currently, I think HLSL is the default, and CUDA or any other primitives can be added through the IHV vendors. But from the ISV vendors, if someone wants to add OGL directly accessing your meta commands or directly to the HLSL side, can we add new language? Is that supported, or it will be supported?
So you asked two questions there. The first one is, in regards to sort of the parity between ONNX and Windows ML, it's our principle that what is defined sort of in the version of ONNX that we claim to support, we have full support for that operator set. There will always be a couple of places where we may not have one particular operator supported across both CPU and GPU, but that's generally a guiding principle. In regards to, well, as a developer, how do I provide that custom operator implementation? That's something that we're investigating right now.
Yeah.
And if you have needs there, I would love to understand them a little bit more.
Okay, thanks.
Thank you.
In the earlier demo, you were using the Surface Pro pictures, and you said like there were 30 images were used for training the model. Were you using transfer learning technique?
So you would have to go talk with the custom vision folks to get an answer of exactly how they used ML techniques to train that model. That is sort of their realm of expertise, and I don't think I can give you an answer to that one today. Sorry.
Okay. Because I was thinking the 30 images are not enough to actually recognize an object, especially like a Surface Pro.
In this case, it actually was. But if you go to the expo hall and look for a big sign that says Theater 2, very close underneath that sign, there's actually a booth with the Custom Vision team. And you can ask that question there, and they would be able to give you a way more intelligent answer than I can.
Okay, thanks.
Thank you.
I think I can actually answer that question, because yes, it's possible to train the model using just 30 images. And actually, Google has a great demo of that on trainthemachine.com, where you can do it in a browser without even GPU. So it's a pretty simple convolutional neural network. My question is, are there any APIs for, let's say, retraining on the edge if you need to adjust your model on the edge for each specific device? And if there are no, are they planned?
So Windows ML today is purely an evaluation API. Sort of conceptually, things like reinforcement learning are things that we think about. I don't have any plans to share with you right now as far as where that is in the roadmap. But these are topics that we're definitely interested in thinking about.
And does it do any batching when you do the inference? So like 5 requests will get batched and parallelized on the GPU?
So The underlying implementation tries to squeeze out the most performance from our direct compute layer as possible. So if you have a specific question there, I'd love to point you out our devs to sort of understand the underlying implementation a little bit more. But in general, we program the GPUs to get as much performance out of them as possible. And the interesting thing is, the Windows AI platform team is actually the same team that owns the Windows graphics stack. So it's the same team that owns DirectX and sort of all the APIs that you use for rendering in your application. So we have a very intimate knowledge of how to program GPUs with DirectX to get the best possible performance out of them.
And how does all of this relate to battery savings and just settings in the operating system to save battery? So if I, for example, select battery saving mode in my Windows 10 machine, would that somehow influence Windows ML, or is it just completely separate thing?
Right now, no. The thing to sort of consider here is that by being able to talk to the GPU using the same sort of DirectX infrastructure that we use for rendering, a lot of the power management affordances that you would expect for rendering, we also get when talking to the direct compute stack. The interesting pivot, though, is, the vision that we have is that we want to see evaluations used more broadly, not only by your products, but like within our products as well. And just like today, rendering with a GPU is pretty much ubiquitous. Like everything you see on the screen is hitting a GPU. We're expecting, ML workloads to be as frequently utilized. So that's definitely an area that we are very keen on making sure that we land properly to not only be as performant as possible, but also make sure that it doesn't impact, a user's battery life and sort of all the other considerations that we have to make when using that resource.
Okay, thank you.
Thank you.
Hi, we played the WinML. We love it. It's great and works
awesome.
Good. And I have a couple of questions in there. One is most of the demos and the samples we played with is all UWP application, right?
Sure.
So how friendly of the WinML to the native environment, right? For example, like most of detection work on the desktop is like UMDF driver or service, right? So is that can be directly integrated with those type of applications?
So just to make sure I understand the question correctly, how friendly is Windows ML to Win32 developers?
Yes.
Yes.
Right.
So in the April 2018 update, there are two flavors of APIs. Like you saw in all the samples, UWP, and we also have a COM layer that the UWP layer actually projects from. In the developer preview, one of our goals was to get both these APIs out there so we can start getting feedback from you guys to understand what changes we need to drive into the API to make this a long-term robust platform for you. So as I was talking about moving Windows ML out of developer preview, one of those goals is to look at that API surface and make sure, both for Win32 and UWP developers, it's as powerful and capable as possible to enable you guys to do your thing, again, either on Win32 or UWP.
All right, great. The second question is, if I want to bring this WinML to the production, release it with my software, right? So any constraints or extra library needs to be attached to it, or would that be automatically generated when we're doing the installer?
So no, this is one of the great problems that Windows ML solves. If you have a model in Onyx, you don't have to worry about deploying an evaluation engine that knows Onyx. Windows is that engine. So if your endpoint that you're evaluating that model on is an April 2018 update of Windows 10 or newer, you don't have to deploy any additional libraries. You just worry about writing your application, focus on creating that model that you want to use to drive your experiences. As a platform, we have the infrastructure already in the OS. We have the ability to talk to the GPUs on your behalf in the OS. You do not have to worry about deploying additional libraries to do that.
Wow, that's great. So the last question is, we talk about the CPU and the GPU, right? So is any mechanism underneath in that to automatically engage with the VPU, right? Vision Process Unit in there?
Sure. Sorry, I missed the last part of the question. I heard VPU. I didn't hear the preceding question.
Oh, it's just is any does the WinML automatically recognize the VPU and then execute what would be the performance compared to the other things?
I see what you're saying. So what we showed at Windows Developer Day was a very early preview of an effort that we're doing to create a driver for such devices. The end goal of that effort is such that when such a device exists on your machine, or a machine that your application is evaluating on, it registers itself with the OS in a way where Windows ML just knows how to talk to that device. The whole point is, regardless of what kind of AI accelerator you have, so long as it implements this new driver model, as a developer, you can just select, oh, I want to evaluate on that device. You can enumerate the devices and select which one you want, but your application code would not change because you're talking to either the CPU, the GPU, or the VPU.
All right, thank you.
You're welcome. Great. Thank you, everyone. Enjoy the rest of the build.